Welcome to this session about building 3D experiences using Jetpack XR. I'm Dereck Bridié. I work on developer relations for Android XR. And today, I'll walk you through the steps of bringing an adaptive app to Android XR and explore ways to differentiate those apps with rich 3D content. Just in case you haven't heard of Android XR already or haven't been able to attend the demo today, let me introduce you to the first unified platform for extended reality devices. Android XR is the newest platform in the Android family. It's built especially for devices like XR headsets, wired XR glasses, and intelligent eyewear, enabling a bunch of new ways to interact with Android apps. In other words, it's an operating system for next-generation headsets and glasses. Samsung Galaxy XR was the first device to run Android XR, which was released in October of last year. Samsung Galaxy XR blends the physical and digital worlds, immersing the user in spatial experiences. I'm sure you're happy to know that Samsung announced that the Galaxy XR will be available in the UK in July. The device launched with a rich catalog of over 100 apps built with Android XR SDKs, in addition to a whole list of existing adaptive 2D apps that just work on Android XR. For example, Fox Sports released an app that lets you stream games and events in immersive 3D right from your living room. And also, our friends at Calm brought their meditation app to XR, where you can dive into a breathtaking world of mindfulness and stress reduction practices. When we spoke to the team at Calm who built this experience, they noted that since they already used Jetpack Compose for their mobile app, expanding it into XR was a really natural choice. I'll quote them. It felt like extending our Android development, not starting from scratch. They were really able to reuse a lot of their existing code base and could dramatically cut down their initial work, building their first orbiter menus on day one and a core XR Calm experience in about 2 weeks. And 2D apps that you're already familiar with can work on Android XR too. Since it's just Android, you can fill its infinite screen with your favorite apps from Google Play. For example, you can access Google apps that have been reimagined for XR. You can create totally new experiences for Android XR, and use many mobile and tablet apps that exist in the Play Store right now. Last month at I/O, we showed more devices that are coming to Android XR. On the left, you can see intelligent eyewear, which includes audio and display glasses that augment the world around you with helpful experiences. And on the right, XReal Aura. They're lightweight, wired XR glasses with optical see-through technology. These different types of devices have different types of experiences that they're optimized for. Audio and display glasses help you in your day-to-day life and are optimized for low power use and augmenting the world around you. XR headsets and wired XR glasses have more powerful immersive capabilities and advanced UI capabilities. In this session, I'll be focusing mostly on immersive experiences and the Jetpack XR libraries that were used to build them. Actually, the apps that you saw before were built using Jetpack XR too. So for immersive experiences, these are the libraries that you'll most likely be using. There's AirCore for Jetpack XR, Jetpack Scene Core, Jetpack Compose for XR, and Material Design for XR. I like to imagine these kind of like as a layered cake, where the first layer is AirCore for Jetpack XR. AirCore for Jetpack XR really brings perceptive capabilities to your XR apps. In other words, it's a lot like information about the real world, such as the location of the hands and the position and rotation of the joints, and where flat objects are, like tables or floors. AirCore provides this information to your app, when granted the right permissions, of course, and really helps your app understand the world around the user. Then there's Jetpack Scene Core, which provides a scene graph and some basic spatial components. This library is capable of presenting entities in 3D space and provides spatial behaviors. And of course, we all know Compose. There's Jetpack Compose for XR, which provides new composables built especially for 3D. It also provides composables that make it easy to bring your existing 2D content to 3D too. And finally, there's Material Design for XR. It provides components that look and feel like they're all at home on Android XR. For example, this list detail view becomes separated panels when in full space. In this session, we'll go through adding spatial capabilities and progressive enhancements to this animal encyclopedia app using these Jetpack XR libraries. As you can see, the app already works great on mobile devices such as smartphone, and also on tablets through adaptive layouts. And we'll upgrade it to look good and feel great on an XR too. Actually, if we just run the app without any modifications, you'll see that it already runs. When you're building for Android, that means you're building for Android XR too. Android XR helps to support apps with little or no changes. To start progressively enhancing your app and add spatial adaptations, we'll check the spatial configuration. The spatial configuration really informs your app as to whether or not the device has any spatial features at all. Then there's spatial capabilities. These capabilities describe whether or not your app is able to hook into spatial capabilities, such as whether or not you can show spatial UI, whether 3D content is enabled, or whether you could play spatial audio. As I showed before, apps that don't make any changes for XR can run in a mode called home space. Home space is really the very first thing that users see when they put on the headset. I like to imagine it as free-form desktop windows for your Android apps, but put on a seemingly infinite virtual display. One of the major benefits of home space is that it enables side-by-side multitasking with other apps. Home space is really good, but it's a 2D surface for your app in a 3D space. To unlock the full power of Android XR, your app needs to enter full space. Full space is the setting where your app has full access to the immersive capabilities of Android XR, including 3D content. When an app enters full space, other apps are hidden, and the app comes into focus, taking up the full view around you. Putting these concepts together, we've got the following table. On the left, we've got the different types of devices, non-spatial, such as smartphone, XR in home space, and XR in full space, and whether or not the device has XR spatial features or can display spatial UI. So for the first row, we've got non-spatial devices such as smartphone. These have no spatial features and also can't display any spatial UI. Then we've got an XR device in home space, which does have spatial features, but is currently not capable of displaying spatial UI. And finally, XR in full space. Of course, it has spatial features, and it is capable of displaying spatial UI. And kind of this little bottom right corner here is the sweet spot that we're going to target in this talk, where I'm going to be talking all about spatial UI and XR adaptations. So first, I want to introduce you to this composable. It's called Space Toggle Button. It really provides defaults for you to get you in and out of home space and full space. And it has recommended defaults like the icon that's being used. So there's this expand icon that signifies that the user can go to full space, and the collapse icon that makes it easy to go to home space. This really provides a familiar experience for your users who know to look for this icon to enter immersive mode or not. Another good way to get started with spatial UI is to use material designed for XR. It has some components like the spatialized alert dialog that displays the dialog with actual depth. And you'll notice that the spatial versions of composables seem very similar to the ones that you're already used to. So these could be a drag-and-drop replacement for the things that you're using already. And here's the app again, but here I've added the material for XR design library components. And you can kind of see that as we enter full space mode, the layout kind of breaks out of the box and into different types of UI elements. On the left, you can see that there's navigation tools that have been added in the left as an orbiter. And the top bar has been popped out into its own panel. And these kind of really give the app its own distinct XR feeling. But for more fine-grained control of your spatial layouts, you can use the Subspace. A Subspace is a partition of 3D space where you can place 3D models, build 3D layouts, and add depth to otherwise 2D content. By default, the Subspace is automatically bounded by the system's recommended content box, which is kind of like a familiar, comfortable human-scale area in front of the user. It's sized to occupy a comfortable portion of the view of the device. Subspace modifiers like fill max size will expand to fill this content too. And these defaults are kind of the recommended way to create responsive spatial layouts that look great without hard-coding dimensions. It's just like the adaptive app story as well. And just like in 2D layouts, the Subspace layouts let you arrange spatial UI in different types of ways. there's spatial rows and spatial columns, which also support alignments and arrangements in 3D to put your spatial UI in just the right place. So I've been talking about spatial UI a lot, but let's go into specifics. What kind of spatial UI really exists? Well, the main one is spatial panel. We've seen it in the Animal Encyclopedia app from before, but this is basically a spatial composable that you can put 2D content into. So I've got the sample code on the left. Here we add the spatial panel into the subspace, which will fill up half the recommended content box. And it has a simple 2D composable tree inside. So this is just a normal 2D box with some text in it. And you can see that in full space mode, we just have a panel with the same 2D content contained within inside. Then in this example, I've added an orbiter. That's this purple box on the left. The orbiter really helps you attach content to a main panel. The design language of the orbiter is that it's a floating UI element that adds context that when it's attached to a spatial panel. So oftentimes, we've seen in other apps that it provides controls like navigation, or if you're building a video player, it could contain controls like pause or go back or skip forward, things like that. Here I've got my example app again, but this time with more advanced capabilities here. So I've actually wrapped the layout in spatial rows and spatial columns. So you can see here, this is the spatial row with 2 panels on the left. Or, sorry, on the panel on the left and on the panel on the right. And orbiters have popped out by navigation to the left. And I've added more orbiters for buttons on the end of the layout as well. And if you know Compose, you know modifiers. Subspace modifiers are really similar, but they're aware of 3D spaces and only work on subspace composables. So some of the ones that you see here are really familiar, like fill max size and alignment. So these you'll know from 2D Compose. But we've also got some special subspace modifiers as well, like this one, which is offset. Offset moves subspace composables in 3D along the 3 principal axes, X, Y, and Z. I've kind of color-coded them here. So in this direction, or in the left to right layout direction, the X value in the positive direction moves to the right. And positive Y is going to go up, and positive Z is going to move away from the user. Then we've got rotation as well. You can rotate these subspace composables using the 3 axes as well. And these are represented by pitch, yaw, and roll. So here I've got an example of what that's going to look like. So when we use the subspace modifier rotate modifier, here we've got no rotation. So you can see the Android bot is kind of facing in the forward direction. We've got no rotation in the rotation values in this example. Then we'll rotate it 90 degrees along the blue axis. So in this example, you can see that the blue axis represents this motion of rotation. So we've rotated 90 degrees in this direction. And this third example here, we've got 180-degree rotation along the green axis, which is yaw. And also, we don't want these panels to stick around in the same place all the time. The user should be able to move them into a comfortable location and at a distance that feels really natural for the user as well. So these panels and other spatial objects can be moved and resized as well. So on the left, we've got transforming movable, which lets the system kind of control how the movement is being handled. And it provides default behaviors, like the user will be familiar with moving their cursor towards the outside of the panel to move it around. Also, the resizable modifier, which gives the panel corners that they can drag around to resize the panels. These modifiers also let you specify listeners, so you can define custom behaviors when the panel is being moved or resized. Back to the example again. I've hooked up the Animal Encyclopedia app here to create a new panel with a transparent background. And you can kind of see that in this example, I'm moving it around a little bit and putting it in the right place. And you can kind of put it wherever you want. And actually, with AR Core for Jetpack XR, you can, as an app developer, save a specific location in physical space and recall it later in a new session. So that's what we call persistent anchors. I recommend definitely check out the documentation on that if you're interested in persistent anchors. And also, speaking of documentation, I've got everything on Subspace modifiers on the developer website. And you're gonna remember this by the end of the session, because I'm going to be repeating it a lot. developer.android.com/XR, all the XR info you could need. So please check it out. So I've talked a lot about panels, but how about another type of spatial composable? I'll be adding a feature to the app that really makes the encyclopedia come to life, and that's the 3D models. So we'll need an asset for this 3D model. And for Android XR, we're really leaning into open standards, such as the glTF standard. glTF is a file format for 3D models, and it supports many of the features that you'd expect to see for 3D models, such as physically based rendering, so your models look really realistic to the user, and animation support through blend shapes and skeleton rigging. So these things will really help you to create models that really look like they can come to life in front of the user. And of course, there's a Jetpack XR component for this as well. It's called Spatial glTF model. I'll go over this code real quick. So it takes the tiger.glTF from your app's asset folder. And with just a few lines, you can already show a spatial composable in XR. Compose will retrieve it for you and decode it into memory, and then you can show the glTF model in your own app. And of course, these glTF models, they're also capable of receiving subspace modifiers, so you can move them wherever you like, or use compose animations to move them around as well. And they're not only loadable from the app's asset folder, but if you have a download from an external URL, something like that, you can also load it from there as well. Then these models, as I'd mentioned before, can also include animations. And you can use compose to control the state of this too. So in this example, we're looking up the name of an animation called roar. And using a disposable effect, we can seek the animation to the correct time using seek_to, and then start it later, and then start it at the exact point of the action. There's also glTF introspection, which we recently released. It's kind of like an advanced capability that helps you find models or nodes in a model and change their properties individually. So here I've just got one glTF. But what I want to do is make the arrows move around without having the cube rotate. So if we were to move this single glTF and rotate it, then you would find that actually the cube and the arrows are moving. But in this scenario, we're able to look inside the glTF and find this node that's called arrows and animate the properties of that one individually. So yeah, we use the quaternion to specify the rotation values and use compose to animate over those values as well. And then got to plug the Android developer documentation one more time. developers.android.com/XR, and we've got everything about 3D models here too, and get you set up showing those in your own apps. Finally, I want to talk about one more type of spatial UI, and this is spatial external surface, and it's hemispherical, which is here on the left. You can see in front of the user that it's kind of like a half sphere that's located in front of the user. This is commonly used for VR 180-degree video. And on the right, we've got spatial external surface sphere, which is a 360-degree surface that's completely surrounds the user. And actually, whether or not your video is on a flat surface or something else, or like a sphere, you can introduce depth to the video using stereoscopic content. So this is kind of like the theory of stereoscopy. Basically, there's two images, and when you display them one to each eye, and offset them by just a little bit, you can mimic depth perception. And this is what's used for stereoscopy. If you've got two separate images, you can kind of just put them together like that, and you've actually created a stereoscopic image. In this example, we've got them on the left and on the right, called side by side. But if you have a spatial video that's on top to bottom, sometimes we call that one side by side too. But that's how, if your video is formatted like that, you'll be able to show stereoscopic content. And in case you have videos that are actually in the MVHEVC format, you'll be able to display those as well. So this is the code for spatial external surface. We're going to be using our friends over at ExoPlayer to play this video. So here we're building an XO player that is aware of our context and that will start playing our video. And we will use the spatial external surface to create this composable in 3D space. And we've specified that the file is actually in side-by-side format. And then when it's ready, we'll connect the player and the surface together and point XO player to the asset that's in our assets folder. And we'll get XO player prepared and ready to play. And then, of course, we'll release all the resources when the player is finished, because you don't want all that hanging around in your app all the time. We've seen the talk on performance just before this one. Here we go again. If there's one thing I want you to take away from this, developer.android.com/XR, spatial video, all about it. So please check that out. Finally, I want to go over the Android XR Developer Catalyst program. So I've talked a lot about these devices, but if you want to get hands-on with these devices, we actually announced the Android XR Developer Catalyst program, which includes our upcoming XReal Aura. And if you want to apply to get one of these, please feel free to apply today, g.co/dev/catalyst. And you may receive an XReal developer kit or an intelligent eyewear developer kit in the next coming months. So please check that out. Right. I'll give you a quick little recap here. We've learned about the libraries in the Jetpack XR family. We've seen how to lay out spatial components in 3D using spatial layouts. And finally, there's everything about 3D models and spatial videos as well.